Welcome everybody to yet another program of IIA Golden Jubilee Celebration. In today's program, actually we have two events. One is the release of the ebook, Women Astronomers of IIA, Reaching for the Stars and Beyond, which is edited and compiled by the Gender Amity Cell of IIA. And the book will be released by Professor Van Dishoeck, President of the International Astronomical Union. And that will be followed by the IIA Golden Jubilee Lecture by Professor Dishoeck. So we will begin with the welcome address by Professor Annapurni Subramania, Director IIA, and then we will have a very brief overview of the ebook by the Chairperson, Gender Amity Cell, and our distinguished speaker will be introduced by Professor G.C. Anupama, Dean IIA, and that will be followed by the release of the book and the IIA Golden Jubilee Lecture by Professor Dishoeck. So may I now request Professor Annapurni to deliver her welcome address. Over to Annapurni.
Yeah, thank you, Aruna. So I welcome you all to this, the second lecture of the concluding session of IIA50 celebrations. So just to give a quick timeline, the Institute traces its origin to an observatory in Madras in 1780s, set up there in Nungambakkam, and it functioned there in Chennai for a very long time. And then in 1890s, it moved to Kodaikanal, as later known as the Kodaikanal Observatory, and started its observations in 1899. And ever since, we have been collecting the data of the sun. And Kodaikanal is very well known for the data and availability of the data for more than 100 years. And this is a treasure trove to study the long-term variations in the sun. And in 1971, the Observatory Kodaikanal was converted into an autonomous institute under the name Indian Institute of Astrophysics. So this year we are celebrating the 50th year of its formation, and the celebrations began on Founders' Day. That is the birthday of our founder. Founder is Professor Venubapu. Professor Venubapu actually oversaw the transition of the Kodaikanal Observatory to Indian Institute of Astrophysics, and he's also set up our Kavalur Observatory after that. And he also set up this campus of IIA Veram sitting, which is in Koramangala. So ever since IIA has grown, and now it has many more field stations, the Southern Observatory in Kavalur, then our radio observatory in Gauri-Bidanur, where we do radio observations of the sun. Then we also set up observatories in the Himalayas in 1990s. And we have 3 stations there, one in Leh, and the 2-meter telescope in Hanle, and our field station on the banks of Pangong Tso, where we plan to set up the next generation solar telescope. And this year, we started off with the activities on the Founders' Day and the activities inaugurated by the Secretary of the TST, followed by several conferences, one to earmark the 20 years of operation of the Himalayan Chandra telescope, then the 5 years of operation of UVIT on AstroSat. So UVIT was led by IIA in collaboration with other institutions, and the Space Science Laboratory in Crest campus delivered this payload, and it is in the sky observing, and it's completed more than 5 years. So looking forward, we have several missions planned. The immediate one being the visible emission line coronagraph on Aditya mission, which will be placed in L1 orbit, and followed by several other missions, which is in the planning phase, as well as ground observations. So this is an extremely important year for Institute, which is a milestone year where we are completing 50 years and looking forward to a brighter future. And I'm very happy to have the president of the IAU talking to us today. And welcome, Ewine, and I welcome you all for this session. And thank you, Aruna. I give back to you.
Thank you, Annapurni. And okay, so moving on to the next item. So I will give a very brief overview of or the background of this ebook, which is going to be released today. So I begin with a warm welcome to all the participants today's August occasion and the Golden Jubilee celebration of IIA. So I will complete 50 years in 2 days from now, and it is a momentous occasion in the history of the Institute and a proud moment for all of us to be a part of this incredible journey. So among many accomplishments, gender diversity has been an important part of the Institute's legacy. And over the years, IIA has maintained a healthy gender balance and produced a large number of women scientists in the country. And many of them have gone on to make exemplary careers as astronomers and scientists, technologists, and educators. The achievements of and discoveries from IIA in the past 50 years span a wide variety of topics in observational and theoretical astrophysics. Now, women scientists of IIA have contributed significantly to the growth and overall development of this institution. And in terms of challenging research projects, mentoring students, and producing a good number of brilliant and motivated astronomers, and also in terms of research publications. So on this occasion of the IIA Golden Jubilee celebration, the Gender Amity Cell of IIA had initiated to bring out an ebook to acknowledge and celebrate endearing life stories of IIA women scientists and engineers. So we had invited them to recount their research experiences and personal impressions during their affiliation with the Institute. Now, the overwhelming response has resulted in a collection of 46 articles, which we are now happy to share with the broader audiences. So in these pages, you will find glimpses of their ideas, ethos that brought them to astronomy and astrophysics, values they uphold, and the message they would want to pass on to the next generation. So we are glad to have with us Professor Ewine Dishoeck, President, International Astronomical Union, who have kindly agreed to inaugurate this ebook. Now, Professor Dishoeck is an eminent molecular astrophysicist, and we are immensely delighted to have her join in our celebration. Professor Van Dishoeck will also give the IIA Golden Jubilee lecture to commemorate the IIA50 celebrations later this evening. I would like to take this opportunity to thank all the contributors for making this book a reality. The book would not have been possible without the dedicated support of many. All the members of the Gender Amity Cell have been particularly enthusiastic about this initiative, and we thank them for their extended support. My colleagues, Professor Ravindra Banyal and Professor Maheshwar Gopinathan, were always there with timely advice and suggestions. Expert help from Dr. Prasanna, Mr. Anand, and Rishabh are gratefully acknowledged, without which we have not seen the book in the present form. Special thanks to the Director and Dean of IIA for their support and encouragement, and we are thankful to many others for their goodwill and support. So this book will be available in the IIA50 webpage, and I hope the readers will enjoy the book. And for me, it's going to be a treasure for years to come. With this, I welcome you all again for today's program. And may I now request Professor Anupama to introduce the speaker to our esteemed audience. Professor Anupama.
Good afternoon, everybody, and good morning to our speaker. So it's a pleasure to introduce Ewine, who is a professor of molecular astrophysics at the Leiden University in the Netherlands. She graduated from Leiden in 1984 and held positions at Harvard, Princeton, and Caltech before returning to Leiden in 1990. The work of her group innovatively combines the world of chemistry with that of physics and astronomy to study the molecular trail from star-forming clouds to planet-forming disks. She has mentored several dozens of students and postdocs and has been heavily involved in planning new observational facilities such as Herschel, ALMA, and JWST. Professor Van Dishoeck has received many awards, including the 2000 Dutch Spinoza Award, the 2015 Albert Einstein World Award of Science, the 2018 Kavli Prize for Astrophysics, and the 2021 Jules Janssen Prize, the last of which is the French Astronomical Society's prestigious International Astronomy Prize. She's a member or a foreign associate of several academies, including those of the Netherlands, the USA, Germany, and Norway. Since 2007, she is the scientific director of the Netherlands Research School for Astronomy, or NOVA. And as of 2018, Professor Van Dishoeck serves as the president of the International Astronomical Union. And as the woman president of the IAU, I think it is she is the most apt person to release the ebook on the women scientists of IAA. I now invite you, Professor, to release the ebook.
All right, thank you very much. I think we're going to see here a wonderful movie. Thank you so much for doing this. So I think we are scrolling here through this book. And I had a preview last night, and it's really fantastic. I want to congratulate you on making this book because it is heartwarming. It is fantastic to see the stories of all of the women scientists, and quite a number of them that have been associated indeed with the IIA. I'm very impressed by that. When I read through the stories, there were some things that were in common. Often there was an inspiring teacher that was an important first step that I read in quite a number of the stories. There was also the importance of role models. And I think now you all in this book actually serve as role models. You all have important messages for the next generation. And that there were also quite a number of you that said how inspired they were by the night sky. I mean, you have a beautiful sky in India. It can be very, very dark, not like in my little country in the Netherlands, where it's very difficult to find any dark place. But you have the beautiful skies, night skies, and that has clearly also inspired several of you in being attracted to this field. Not just the night sky, I think also the sun. I think India has quite a number of solar astronomers, and especially also female solar astronomers. So I think that's another thing that you see here in this book that comes through. I'm sure that this book is going to be an inspiration for the next generation, and I really congratulate you on making this. In 2017, as the executive committee of the IAU, we visited actually India. We visited Pune, Ayuka. And one of the things we did there was actually organize an afternoon on women in astronomy. And that was a very good occasion in stimulating there in that area and that institute also the importance of having female role models and having active participation of all the genders. So it's great to see that, and again, my congratulations on producing this wonderful book. I now see also the cover, and that's a beautiful cover. So I encourage everybody of the Institute, but also beyond the Institute, to take a look at this book. And perhaps we can also promote it through the International Astronomical Union. Yeah. Good.
So thank you, Ewine, for your kind words, and I hope everybody will like reading this book. And moving forward to the next item, we will now request you to deliver your lecture. Okay.
Right. Yes. Okay. Good. So you can see my screen. I assume that is okay. So it's a pleasure to be here. I wish I could be with you in person. I visited India a couple of times. And in fact, the first time I visited India was in connection with the General Assembly of the IAU in 1985 in New Delhi. And actually, I read in some of the stories how important that General Assembly actually was also for Indian astronomy and also for female astronomers in India, because they had an opportunity to meet with so many foreign colleagues by coming to New Delhi. And that was followed actually by a symposium on astrochemistry in Goa. And we traveled through India, through Rajasthan with a group of astronomers. And that was also a wonderful experience. And then indeed I came back in 2017 to Pune and visited their IIA50. But I want to congratulate you with your beautiful observatory, your very strong observatory. I always heard from my colleagues about Bangalore and how important it is. And of course, Vanu Bapu as the former president of the IAU, also being a towering figure in astronomy. Good. So we're far away, but yet I think thanks to the wonders here of these virtual meetings, we're actually more connected than ever. So as hard as this lockdown is on everybody, I hope that you're doing well and that together we can still contemplate our beautiful and celebrate our beautiful little Earth, as you see over here. Continuing still on the previous topic, I actually collected a few statistics on female members of the IAU, just to give you an impression as to where India stands. And it's actually interesting to see. So this is sort of in decades over the years since the start of the IAU in 1990. And you see it started with sort of 10% level, then actually after the First World War, it went into a dip, into an extremely low fraction. Primarily, male astronomers were hired in that period across the entire world in university positions. And it's only in more recent years that this starts to be increasing again. And we're now sort of close to 20% if we include now also our junior members. All of these numbers are actually on the IAU website that you can check them. But I like this distribution, this graphic distribution actually better. You can find it also in our strategic plan of the IAU 2020-2030, which is posted on the IAU website. This was the situation in 2015. And one of the reasons for raising this topic here in India when we visited as the IAU Executive Committee was that India was particularly low in its female fraction, between 1 and 10%. You see that most of the Western world is still very low, only between 10 and 20%. It's only some of the more southern countries in Southern Europe and in South America that are more at the 20 to 30 and 30 to 40% fraction of female staff members. So to become an IAU member, you have to have a long-term prospect in astronomy. So usually it's not at PhD level or at starting postdoc level, but a little bit later. But then in 2018, I was delighted to see that India had changed its color from blue to green. So now it is also in the 10 to 20% category. And in fact, I just looked at the very latest statistics here now at 17% India, which is actually very comparable to many of the Western European countries. So you are actually well on the way to becoming yellow in the not too distant future, especially with these inspiring stories that you have. So congratulations again on that. Right, so I'm going to talk in my lecture about the origins of stars and planets. And I just want to remind you all also of the importance of the inspiration that astronomy brings. Again, you see it in the stories that women have. We see it in all of the outreach that you do. And in fact, India is particularly strong also in outreach. You're doing a lot of efforts in that. And the good thing is that this is available to anybody, anywhere in the world. And as you see here, even with social distancing. And just looking up at the sky, you cannot help to wonder as to where do we come from and what is our place actually in this universe. And so in 2019, the IAU celebrated 100 years of its existence, and we carried out some 5,000 activities in more than 143 countries. And India was a very active participant in many of these activities. And again, also because of the dark and quiet skies that you have. And so I encourage you to still browse a little bit through this report. Also, you got an exoplanet named actually as part of this celebration through a public campaign. And that is one other way of very actively engaging with the general public. Good. So after this sort of introduction, I would then like to turn to the main topic of my presentation, and that is the zooming in into the regions where new stars and planets are being born. And this is especially thanks to the advent of the Atacama Large Millimeter array that this topic has really taken off. And I hope to give you a little bit of a taste of this field. I know this is not a field that is that very active in India, but I hope that in this way I can give you a little bit of a feeling as to what is happening actually in this very exciting field that is especially attracting a lot of young people. It's, of course, very closely linked with the exciting field of exoplanets. We know that that is one of the fastest growing research topics in astronomy. We now know, thanks to the Kepler mission and through the radial velocity surveys, that on average, every star has at least one planet, but that they are of a type that we do not necessarily have in our own solar system. Most of them are actually so-called super Earth or mini Neptune, somewhere between 1 and 10 times the mass of the Earth. And even though exoplanets had been speculated about for centuries, it was not until the discoveries in 1995 that the field really became a scientific endeavor, and that was, of course, awarded with the Nobel Prize in 2019 for Majore and Collas. But equally important is what sets this diversity. This diversity must have been set, this diversity of planets that we have must have been set already at the formation stage. So how do they form? What is actually their composition? And could they be habitable? Do they have the material, actually, for example, the water, to make them habitable? And directly related to that is also the question of our own solar system. How did we form some 4.5 billion years ago? And we can get information about that from the remnants of the formation of our own solar system. In the inner solar system, that is the asteroids, and there have been just 2 missions to asteroids, Hayabusa by the Japanese and OSIRIS-REx, and they have collected a little bit of material, brought it back to Earth. In the case of Japan, it has already landed, and that can now be studied in a laboratory on Earth. And also the meteorites, of course, that fall on Earth are very important messengers of the inner part of our solar system. The outer part, we have the comets. That's not just rock, but it's actually a mixture, about 50% ice plus rock. And here several missions, but most recently the Rosetta mission that had actually for the first time landed on the surface of a comet 67P has actually provided a detailed information on the composition of one such comet, and again providing information on the conditions some 4.5 billion years ago. So both of them messages from the early solar system, with the comets being the most primitive material that is still left over. Now we know about interstellar clouds, and they can be stable for quite some time, but in the end, gravity takes over. And that means that the cloud will actually start to collapse under its own weight, and it will then form a protostar in the center. But because the cloud always has a tiny little bit of rotation, it means that the material cannot continue to fall in radially, but part of it will actually come into a rotating disk of gas and dust around the young stars. These disks actually were predicted already, again, centuries ago. Immanuel Kant speculated about them. Swedenborg speculated about them. Of course, also the planets in our own solar system, they all lie in one plane and they turn in the same direction, again, suggesting that they originated from a solar nebula, as it was called at the time. This is actually what we can now start to study. So the first evidence for the existence of these disks came in the same year actually as the exoplanets were discovered in 1995. It was a very exciting year. This was, among others, from these kind of images of the Hubble Space Telescope. Where if you looked very carefully with a magnifying glass, you could see that these young stars that you see over here, they were surrounded by these dust disks. The dust, of course, consisting of silicates and carbonaceous material. And here you see them sort of in a face-on situation, whereas here you see them in an edge-on situation. And these images were important because they also gave sort of the size of these disks. And this is roughly the size of our solar system if it were at that distance. And so you see that it is indeed about 50 to maybe up to 100 astronomical units, the size of these disks. Then, 25 years later, came another iconic image, and this time with ALMA. I'm sure you've all seen this image taken by ALMA in 2015. For a long time, we thought that these disks, especially these young disks around stars, would be very smooth, with very little structure. But when this first image came from the long baseline campaign of ALMA, everybody was just amazed by the structure that was seen in these disks. Now, one should realize that the contrast is not very large here, so these are indeed dark lanes, but the contrast is only at the level of about 50%, so they are not very deep rings, as you see over here, but nevertheless, they were important because they showed that they were present there. They were likely, at least some of them, due to the presence of forming planets there. And again, we were looking there at the size of our own solar system. And this has been made possible by ALMA, which is the first worldwide collaboration in astronomy between North America, Europe, and East Asia. Together, they put this array of some 66 telescopes on a high altitude plateau in northern Chile, as you see over here. Now, ALMA observes at millimeter wavelengths. You can think either in gigahertz or you can see in millimeters. But just to say a few words about the main physical processes responsible for the emission, the continuum is primarily due to thermal emission from cooled dust grains. It's only at the longest wavelengths that you may start to pick up some of the free emission that you're all familiar with in your radio astronomy. Whereas the lines, and there are literally thousands of lines in this wavelength range, those are due to the end-over-end rotation of the molecules in space. So these are the pure rotational transitions of the molecules. And just to give you sort of the impression of the power of ALMA, this was an image that was obtained with the pre-ALMA array, one of the pre-ALMA arrays, the submillimeter array on Mauna Kea, and that was painstakingly obtained over a number of nights. And this was ALMA in cycle 0 of the same disk in just 20 minutes, when ALMA had only 16 antennas at the time. So this shows already the power of ALMA and also the image fidelity that we would able to get. Keep this image in mind because I will come back to it later in the talk. Well, actually, after those first images already signaled a new era in I would call observational planet formation. This was actually one of the first images that our group got in 2013, which was at the same time wonderful, but also utterly surprising. We had expected to see a full disk here. Again, we had expected to see one of these smooth disks, maybe with a cavity inside it, and instead we found this very, very asymmetric peanut-like image that we obtained there. What we are seeing here is actually what is called a dust trap. I'll come to that in just a moment. Then after this image came the HL-Tau image, which of course has now become famous. And then there is another one of a very nearby disk where actually was able to go down to 1 astronomical units. And then more and more on an almost daily basis, you see these images with cavities, rings, what you see sometimes spiral arms, that you can see not only in thermal emission, but also in scattered light here with the near-infrared instruments on the various telescopes. So what are we looking at actually? Well, we're looking here at what is called the dust trap. And this is very interestingly an image that Fred Whipple made already in 1972, then of the solar nebula. He called it the Laplace Nebula. And he realized already that because of the gas is supported, of course, by the thermal pressure. I mean, both gas and dust are in Keplerian rotation around the proto-star, the proto-sun. But the dust is just feeling the Kepler's laws, whereas the gas has a thermal pressure component. So there's a slight difference in the velocities of the gas and the dust. And this also causes a little bit of friction, but it means that the dust will actually move towards the pressure maximum and it will actually start to collect there and it will grow to larger particles here. So we call these particle traps. They happen at the pressure bumps when you have a planet going around in a disk. That will actually create here a pressure bump just outside, and that is where these dust particles will collect and form a particle trap, a pressure trap. And this is really where then these particles can collide and grow without too many destructive collisions, and they can grow and grow to larger planetesimals that eventually become the building blocks for planets. So these are good positions where you might form planetesimals and the building blocks basically for planets. Now, after these first images, then was 2018, there came this wonderful large program of ALMA that is called Dishoeck, led by Sean Andrews from the Center for Astrophysics. And they targeted the 20 brightest disks with ALMA at the same resolution as HL-Tau. And you see here all of these structures in these disks. There's, in fact, maybe only one smooth disk in this whole sample. The bulk of them, basically all of them, have one form or another of structures, either rings, sometimes even spiral structures, etc. But still, this was a biased sample. How common are these structures? What do they actually tell us? Are they in all cases indeed indicative of ongoing planet formation? How do they actually fit in the general disk population? Because again, these are just the 20 brightest disks. And then from my perspective as a chemist, I'm also interested in the chemical composition. So more generally, what my group is trying to understand is when you collapse such a cloud, dense cloud to form an accretion disk, basically what are the various molecules that are formed there, both simple molecules and sometimes more complex molecules. And one thing that we're learning now is that a lot of this planetesimal formation that I just talked about happens not only in these mature disks, but likely starts already at an earlier stage in even the embedded stage of planet formation. We call this early stage the class 0 and the class 1 stage. That's just based on their spectral energy distributions, whereas the other ones are the spec 2 stage. So just to give you a tiny little flavor of the kind of chemistry that is happening, I want to talk about one of the most important molecules, namely water. And thanks to observations with the Herschel Space Observatory and also laboratory experiments carried out in Leiden and elsewhere, we now think that the bulk of the water is actually formed in the following way. There we have a tiny little dust grain, and maybe once a day a hydrogen atom actually arrives on that dust grain. Yeah, there it comes. It will scan the surface of the grain, it will find another hydrogen, goes off, and that is how we make molecular hydrogen in the universe. But it can also find an oxygen, the red ones. And then here we make actually a little bit of molecular oxygen. We can make actually hydrogen peroxide there. Yes, there it comes. And now we can make actually 2 water molecules. And now we fast forward this process over maybe 10,000 years, 10 to the 5 years. And that is how we make more and more water molecules. And we actually form an icy layer on the surfaces of these dust grains. And so if you ask, where does most of the water on Earth come from? Where was it made? Then it was actually made in the cloud, the interstellar cloud, like you see over here, out of which our solar system formed, already in the pre-stellar cloud prior to collapse. And so one of my colleagues actually said, the water on Earth is actually older than itself. So think about that the next time you drink a little bit of water, that the water molecules that are here in this glass are already 4.5 billion years old. And since that time they have evaporated and recondensed again, but the bond between the atoms, as you see made over here, that happened already in the cloud out of which our solar system formed. So what I will not talk about is that you make not just water, but also other more complex molecules on the surfaces of these grains. And this is just a sample of chemistry, simple molecules, but also more complex molecules, propanol, acetone, etc. Some of them you may know from your daily life. Also some prebiotic molecules like this C and O bonds that you see over here, beginning of peptide bonds with metal isocyanate, and also some other nitrogen-containing molecules that we now find a little bit routinely now, this ALMA, in regions in which solar mass protostars are forming. It's not just only Orion or Sagittarius B2, the giant molecular clouds, the very massive stars that are forming that have a rich chemistry associated with it. It's actually also these solar mass normal stars that form. So I will talk about from disks to planets then, from what is basically the typical planet-forming disk. What are their properties if you want to understand sort of this diversity in exoplanets that we now see. So I will talk primarily about disks around the pre-made sequence star, what I called the class 2 phase. I'll talk a little bit about the surveys and the dust statistics that we have done. Just only a few words about the chemistry, and then come back to these so-called transitional disks, these disks that show cavities, rings, and the importance of snowline in setting sort of their characteristics. I really acknowledge here the work of the very talented students, postdocs, and collaborators that I had the pleasure to work with. I want to mention especially Megan Ansdale, who was not my student, but student of Jonathan Williams in Hawaii, but was leading and co-leading one of the programs. Nienke van der Marel, who read a lot of the transitional disks, and various other PhD students. So prior to ALMA, this was sort of the picture that we had of circumstellar disks. So in the early stages, they are flared simply because of the illumination of the surface of the disk by UV photons. UV photons heat the gas, and then just through thermal equilibrium, hydrostatic equilibrium, they will actually start to flare up, like you see over here. But then with time, the dust grains will collide with each other, they will grow, and they will start to settle to the midplane. And because of this slight difference in the velocities between the gas and the dust, they will also start to move radially in the disk. They will start to drift inwards here to the very close to the protostar. At some stage, a gap will open in the disk. How that exactly happens is still a question. But then photoevaporation will take over. The radiation, UV radiation, will actually set up an evaporative flow, which is faster than the accretion flow, and that will actually then deplete the disk of the gas in the small dust grains. And in the end, you end up with a so-called debris disk that is then gas poor. So I will talk primarily about these early stages, but the important thing is that this was a cartoon prior to ALMA, and now with ALMA, we can actually start to characterize and quantify each of these steps. Now, ALMA can say a lot about disks, but by itself, it's not the only instrument that is important here. ALMA can survey sort of the bulk of the cold midplane, down to sort of the inner, say, 5 to 10 astronomical units. But such a disk always has a radial gradient in temperature, just because the star heats it, and also a vertical gradient in temperature from the surface to the midplane. And so the surface layers and the inner part of the disk are much better studied at near-infrared and mid-infrared wavelengths. So here you see actually how these various wavelength regions actually can complement each other. And earlier you were talking about the UV missions that India is involved with. Well, UV optical, that is very important here to study the stellar properties and the accretion properties that we have. So this also goes very nicely hand in hand. So what we've been able to do as ALMA is actually go from detailed studies of just a few of the brightest disks to actually to very large samples. And we wanted to really ask the question, what sets the exoplanet characteristics? I showed you earlier the fact that most of these disks are actually super Earths and small Neptunes, relatively few giant planets, and maybe here a dip once you go to the Earth. And also there's a clear increase in the number of stars with giant planets if we go with stellar mass. So these are important topics that we need to understand. And so we started this work with the so-called Lupus ALMA disks survey that was led by Jonathan Williams from Hawaii, and these with myself and Leonardo Testi as co-PIs. And then here a number of people students that did very important work, and also later on many others that contributed there. And there's been about a dozen publications from this survey. So we actually, very simple, thanks to Spitzer and the Herschel surveys, we know all of the young stars with infrared access in a star-forming cloud. So take here the Lupus molecular cloud, it's at 150 parsec. It goes right overhead of ALMA, so it's perfectly placed on the southern sky. And in this dark cloud, there are more than 100 young stars with infrared access. So we decided to just target each of them. Here is the distribution. Of course, most of them are low-mass stars, M and K type stars, only very few high-mass stars. And so we decided to target all of these with just 1 minute each with ALMA. So this is really complementary to detailed structure studies that take hours of observing time. This was just 1 minute each. But within 1 minute each, you can already get very high signal to noise on the continuum down to about 20 astronomical unit resolution, which was already much better than any of the pre-ALMA arrays. And you see here sort of postage stamps of all of these sources at a 2 arc second by 2 arc second resolution. So that is a few hundred AU, what you see here on the side. And you see that there's clearly a number of bright, big disks that are actually spatially resolved. We see already some of these transition disks with cavities very clearly. And also quite a number of small disks. These are basically unresolved at this particular resolution. This was actually in the 330 gigahertz continuum or 0.8 millimeter wavelengths. This is at 1 millimeter wavelengths, 1.3 millimeter wavelengths, where we had the same survey to get 2 frequency points. And this is a little bit more complete, adding also some archival data, where we have the complete sample of nearly 100 sources in which was detected. In fact, the bulk of them are detected in 1 minute. Again, you see the same here. Sometimes this is slightly higher resolution. So what usually looked to be maybe an edge on disk actually turns out to be a binary here, a little binary that you see over here. But overall, the quality of the data is actually extremely high in just 1 minute of integration. Now, what can we do with this data? Well, in the simplest form, we can assume that the emission is optically thin. It's thermal emission at a certain dust temperature with a certain dust opacity, and that gives us directly the mass of the disk. And we can do that, and we can plot them in the following way. And I'll just show this to you because all of the plots will be shown in a similar way. What you have here on this scale is actually the dust mass in Earth masses. So this is 10 Earth masses, 100 Earth masses. And this is cumulative, so it's the number of sources that have a disk mass that is greater than this one. So if I take here 10 Earth masses as a typical dust mass that is needed to make the core of a giant planet, then you see that here in Lupus, which is the blue, then there is about 25% of sources that have that disk mass. If I go here to less than an Earth mass, so we see that we have a sensitivity that comes even close, starts becoming close to even lunar masses. Then you see that then you get to close to 100%. So not all the sources are detected. So what you see here is not just our survey in Lupus. Around the same time, there were a couple of other similar studies being done, one for Chameleon by Pascucci et al. And one in Upper Scorpius by Barteveld et al. And what you see is actually that it's a remarkable similarity between, say, Taurus, Lupus, and Chameleon in this distribution. But that when we go to a somewhat older population in Upper Scorpius, then actually you see that it is shifted. There's much less material available. All of these studies assume the same dust mass opacity coefficient. Well, this is already an important conclusion because this means that the bulk of the disks in Lupus can no longer form a giant planet. Either that has already happened or giant planet formation is very rare or a combination of both. And in fact, if we now look at the earlier stages, these embedded phases of star formation, which we call the class 0 and the class 1s, then this was actually done with 9 millimeter data to make sure that we were in the long wavelengths in the optically thin regime with the VLA, then you see that there is actually a shift here. There's much more material available in the early phases. So the mass decline really starts very early. It goes from less than 1 million years to a few million years to 5 to 10 million years. Goes very quickly. Implication is that because by this stage we no longer have enough material available, that it must start already early. And that is better visualized in this figure here from my former PhD student Lukáš Tekoniec, where he actually looked at the exoplanet catalogs, looked at the mass of the solids in those exoplanets and just plotted them all as a function here of stellar mass. And then this is where the young disks in the embedded phase lie, and class 0 and the class 1 phases. And this is where the mature disks actually lie, the Lupus type of disks. And you see that these are not enough to explain the bulk of the exoplanets. We can do it in the young phase, and then we actually have a required planet formation efficiency. How much of my disk mass do I have to turn into planets? That's about 15% in the class 0 stage and about 30% in the class 1 stage. So interesting numbers for people who do planet formation to keep that in mind. Now, there are also some environmental effects. We saw that Lupus and Chameleon are actually very similar at Taurus. These are all very dark clouds. How about if I am in a high mass star forming region, if I'm close to a massive star like in Orion? For example, here close to Sigma Orionis, an O9 star. And this is also where we did a survey. And not as many disks, but still a good 50 or so of them. And there was a clear jump that we saw that the dust disks were only found more than 1 parsec away from the O9 star, and the gas disks found only 2 parsecs away from the O9 star. Those are the blue ones that you see over here, and the red ones, orange ones are the dust disks. We saw the same thing also in Orion. This is a wonderful vista image in the infrared of the Orion Nebula. Here you see the familiar trapezium stars that you all know in the Orion Nebular Cluster. Here you see the integral-shaped filaments, OMC2. And this was actually an archival data from ALMA taken for a totally different reason. It was just mapping this entire cloud in one particular molecule. But of course, with the broad bandwidth, you get the continuum for free. And we could basically exploit that continuum to do an unbiased survey of disks around low-mass stars in the Orion molecular cloud. And very interestingly, we found that that follows just the lupus one. This survey was not as sensitive, but it came very close. It actually was nearly the same one. In contrast, if we looked at the Orion Nebular Cluster, the trapezium stars, and the disks close to the trapezium stars, they were again clearly shifted. So here we see really that UV radiation photoevaporation is important. You can even calculate from this difference a mass loss rate. That is happening over sort of a few million years in order to deplete these disks, happening already again quite early. So the planet formation potential of these disks is much higher than that of if you're close to an O-type stars. And just before ALMA closed down, we actually were lucky to get something really big. The SODA, it's called, the Survey of Orion Disks ALMA, led by Sierk van der Wischa, former PhD student, where we had not just 100 disks, but we actually had 880 disks. So now we have really large statistics that we could survey in Orion. And the bulk of them are again detected, and we find the distribution that is now with a very small statistical uncertainty is again very similar to that of lupus, which is the red one here in this graph. And again, we can compare with the embedded sources in Orion. This is work from John Tobin, and again, you see the shift here between the early stages and the late stages. So all of this pointing to the fact you need to build planets early, and you need to do it fast. Now, so far I've only talked about the dust. I'm a chemist, so I was interested in molecules, and I thought we would see lots of carbon monoxide and other molecules in these disks. So here are again our 14 brightest disks in the dust. But to our surprise, the carbon monoxide was actually very weak. If I look here, the brightest disk, this disk is bright in the continuum. It's also bright in the gas, but this disk is bright in the continuum. It's actually very weak in the gas. And you see other examples that are bright in the continuum, weak in the gas, and sometimes bright in the gas and weak in the continuum. So clearly, gas doesn't follow the millimeter size dust. And this was actually quite a puzzle, and together with Anna Miotello, we worked on that. The bulk of the disks actually have gas masses, appear to have gas masses that are less than a Jupiter mass. So we would never even be able to form a Jupiter planet. We don't have enough dust, but we certainly don't have enough gas in order to make another Jupiter-like planet. Now, is there really so little dust, or is there just, is there really so little gas, or is there simply so little CO? That was the question that we actually tried to tackle. And this is, to cut a very long story, probably more than 5 years of work short, the answer is that, well, likely they are still gas-rich, but we are not seeing them in carbon monoxide because the carbon monoxide is transferred on timescales of a few million years. Here's 1 million years, 3 million years, 10 million years. This is the carbon monoxide abundance. Here it is high. Here it is very low, and this is where the carbon monoxide has been transformed into chemically. It's transformed into methanol, it's transformed into carbon dioxide, and it's transferred into hydrocarbons. So young disks are still bright in the carbon monoxide, and that's indeed what we see. Old disks, most of the carbon monoxide is missing, but not the gas. And so that is then an important conclusion. So we now have a picture actually of one of these planet-forming disks. where, we have grains that have grown already to larger sizes that may have drifted in. They are pebbles, they are ice-rich, they have a lot of oxygen contained in the ices. Your left here is a gas that is depleted in carbon and oxygen because that has been locked up here in the ices. But because the ices are oxygen-rich, water has more oxygen than carbon, CO2 has more oxygen than carbon. It means that the gas may actually be carbon. And so when you make a giant planet here, actually in one of these regions, it depends really on whether you're making your heavy elements, you get them mostly from accreting pebbles, or whether you get them from accreting gas, because in the one case they will be oxygen-rich, in the other case they will actually be carbon-rich. Important point here is that the bulk of the chemistry of planet formation is actually hidden from our view, because they are already all locked up into these larger bodies. So if you want to study the chemistry of planet formation, you have to go to the early stages, and a lot of this has not yet happened. In the last sort of 5 to 10 minutes, I want to say then something about going back to the substructure and the snow lines. And sort of now the relation between what we've seen sort of in these larger statistics with these detailed structures that we saw in some of the beautiful high resolution images. So here we actually have a gallery of potential planet-forming disks, and we call them the so-called transitional disks, which have these deep cavities that you see over here, and which may be indicative of planets forming there. Let's look just at one of them, just zoom in. This is the source that I actually showed at the very beginning, which looked very lopsided. Well, it is not lopsided. Here's the image that I showed at the beginning. It's actually not lopsided. Now we go to a higher resolution image and look at that. It's a beautiful symmetric ring here, but it's again one of these dust traps, one of these very asymmetric dust traps that we have over here, and that may be the sites of planetesimal formation and planet formation. Interesting, you see it also move actually, that vortex. This is at the higher frequencies, this is at the lower frequencies. You see that vortex actually moving with wavelengths, which means moving with grain size. And that's a very interesting trapping phenomenon. We have probably a vortex over here that is caused by a Rossby wave instability in this particular disk. More generally, we find, if we also look at the gas, that the gas and the millimeter dust do not follow each other. Usually the gas is actually sitting inside the dust cavities. The gas cavity is always smaller than the dust cavity, and we can quantify that now through a detailed modeling, also how deep these cavities are. We are depleting the gas and the dust by factors of 100 to 1,000. And all of this, both the fact that the gas is sitting somewhat inside the dust ring, plus the very deep drops that we have in both the gas and the dust, really point towards the presence of a planet actually inside these cavities. So these are the best candidate disks actually for hosting a very young planet. Often that planet has not yet been seen by direct imaging, but with future ELTs, TMT, this is where you should look. This is where you are most likely to find your young planets. We can also characterize these transitional disks now as part of a disk population, because we know in lupus, they form about 10% of the lupus disks, at least those with a resolution that we have there, more than 20 astronomical units. And that's an interesting number because it's a little bit larger than what we find, say, the few percent of giant exoplanets at those distances. Of course, the exoplanets could have migrated inwards from a somewhat larger distance to the inner disk. But these transitional disks are really among the most massive and also the largest disks that we have in the sample. So they're certainly not typical. And in fact, if you look at the population, it may well be that there's only a small fraction of disks that are the most massive ones, often also around the most massive stars that are very large, that then open up a cavity, maybe because a planet is formed and that then go into these few percent of giant planets at large distances. The bulk of the sources actually goes through this route, small disks that basically fade away. And a big question is really as to what the planet formation potential is actually of these smaller disks. In fact, some of these smaller disks are only small in dust. This is one of the most extreme cases that we have, where we have the dust disk that you see over here in the millimeter, whereas here we see the gas disk. Nicely in the moment one map is the Keplerian rotation, basically a rotating disk. And the ratio of the gas size over the dust size is of order 5 in terms of the radii. So this is really sort of a smoking gun evidence for this process of radial drift, that these millimeter-sized grains, they basically lose angular momentum, they drift inwards towards the star, and they form then a very small dust disk, whereas the gas disk is still much larger. Now, how does this disk now compare with the D-sharp sample? So remember again that that sample, which shows these beautiful images, is among the largest and the brightest disk. Our disk is more, this disk, CX tau, is more representative of the smaller disks. So if I look at these images, these beautiful images, and I take a cut among the major axes and I just plot their radial distribution, then you get, you see all of these dust traps and all of these disks. So these are these 20 disks. This is our disk, same resolution, same sensitivity. And you see that somehow this never formed a trap. It really is a smoking gun of radial drift where the material moved inwards. So the next step is clearly to link exoplanet and disk compositions. We are now starting to probe the disk compositions, and we want to link that with the exoplanet population. And so this is a very active field now, both from the observational perspective, also from the modeling perspective, because now it depends really on where do you form your planet, when do you form it inside an ice line or outside an ice line, and do you actually attract those icy pebbles, or do you attract mostly the gas where you get your heavy elements in your planet atmosphere? This is where JWST will excel, so we're really looking forward to the launch of JWST later this year. We have a guaranteed type program on measuring sort of the inner disk composition. The Netherlands actually built part of the MIRI instrument, and so we're really looking forward to seeing the jump compared with, say, Spitzer is huge in seeing all these elements actually in the inner disk that we can then relate to exoplanet compositions. So I'll stop here and leave you sort of with the main messages that we are unraveling at this very moment the structure of protoplanetary disk with ALMA, both in terms of detailed studies of individual objects as well as large samples of disks to get the disk population. We are characterizing sort of the evolution of these disks on 1 to 10 million year timescales. The UV clearly matters in that. Planet formation must start early. There are a lot of substructures in disks. They're not necessarily related to snow lines, although snow lines do play a very important role in the chemistry. So I'll leave you with this image here as how a disk, no longer a smooth disk, but a structured disk, how that in the end actually determines the outcome of what we have in terms of planets. Thank you very much.
Thank you, Ewine. It was an excellent talk. Amazing slides, beautiful pictures, and a very very nice overview of protoplanetary disk. And I'm sure from the audience, we'll have many questions. Would you like to take them?
Yes, sure. Please go ahead. I look forward to seeing them.
So, Firoza,
yeah,
you have a question? Please go ahead.
Yeah, thank you, Professor Dishoeck. It was a really good talk. My question is regarding the slide where you show the distribution of icy pebbles and dust in the disk. From what I note, the icy pebbles are formed and appear to be accreted fairly close to the host stars, whereas you have the the dusty grains further out. I was wondering why the icy pebbles basically would be so close to the host star. Wouldn't they have evaporated off a long time ago? It seems to be almost counterintuitive. Yeah,
so that is actually, let me just see whether I can go back to this last slide. So basically the snow line of water in a Titori star, so around a LOMA star, is at only a few astronomical units. So it's only at sort of 3-4 astronomical units where the water snow line is. It's carbon monoxide and nitrogen are much more volatile, so they will evaporate further out. But the water snow line is rather close in, actually.
Okay.
Yeah. And then, of course, the silicates, so this is about 100 Kelvin, 150 Kelvin. The silicate sublimation line is closer to 1400 Kelvin.
So also then you show that there's this UV radiation coming out from the host star, which ends up basically disintegrating the material in the outer part of the disk. So how is the UV radiation being shielded in the inner part of the disk? Is it being shielded at all?
Yeah, that's a good point. So there's a lot of debate on whether some of these disks have what is called puffed up inner rims. So you can imagine if there's a little bit puffing up of this inner rim over here, just right at the silicate.
I understand. Okay. Near the silicate line, yeah.
Then it would actually shield some of the UV radiation. But we know certainly the part that is coming here from the accretion shock will be able to reach the surface of the disk unhindered.
Okay, I see. Okay, thank you.
Swastik, you have a question?
Yeah, go ahead.
Swastik, we cannot hear you.
I'm not hearing.
We are not been able to hear him.
Hello, can you hear me now?
Yeah, we can hear you. Yeah, please go ahead.
Yeah, so I just wanted to know, can you study polarization of this disk in radio using ALMA? If yes, what additional information can we have from this disk?
Good question. So you can study polarization both in the continuum and in the lines. Of course, in the continuum, you're looking at the polarization of the dust. People were looking actually for alignments in with the magnetic fields. Because of course magnetic fields play an important role in the collapse of the system. It turns out actually that at the wavelengths of ALMA, we're looking primarily at self-scattering rather than the polarized emission. And so that a very different interpretation than we had before. And so, in fact, in the end, it tells us something about the size of the dust grains that we have in the disk. So that's also interesting information, but different from what we expected. Another line of investigation is for the Zeeman, the molecular lines. For example, the CN molecule that has an open shell system where you can look for the Zeeman splitting. And there we have limits so far, no detections yet. But all of this is, of course, aimed at finding both the magnetic field strengths and also the orientation.
Okay, yeah, thanks.
I think Maheshwar, you have a question?
Yeah,
please.
It was a nice talk. Thanks. So my question is, what are the factors that determine the migration of planets?
Yeah, that's a very good question. I wish I knew. And I've been listening for a long time and also collaborated with people that do planet-disk interactions. There are different types of migration depending on the size and the mass of the planet. There's so-called type 2 migration and the type 1 migration. So the type 1 migration is just moving inwards, is going very fast. Type 2 migration is when you really carve a gap, and the planet is massive enough to carve a gap, and then it will not migrate so much. Certainly not that you then also make a dust trap, and that stops also the migration, also from other planets from further out. But I've even seen cases in which the planet could move outwards instead of moving inwards. So, and that's of course all in the gas-rich stage of the disk. Once you remove the gas and you're in the gas-poor stage, in what we call the debris disk stage, then you can get planet-planet interactions. It's Kozai-Lidov type resonances that can move a planet from the outer disk to the inner disk. So it can happen both in the gas-rich phase, and it can happen in the gas-poor phase.
Thank you.
So I think Manika has a question. Manika? Yeah.
Hello.
Please.
What causes the formation of particle trap regions?
Yeah, I mean, that's a good question, because I showed the main, one of the leading candidates, which is that you have planets in a disk that generates a pressure bump in the gas surface density distribution. That's, of course, a little bit a chicken and the egg problem, because you then first need to have a planet to do so. It turns out that you only need a relatively small perturbation of the disk surface density structure. So I was talking about factors of 100 to 1,000. At 20%, just a little bit like a zonal flow that you would have on the surface of a disk, could already be enough to trap to create such a dust trap. So dust trap is really an enormous exaggeration of what the gas surface density profile would do, and that may show only a very minor variation. Also, it could be triggered, for example, at the edges of dead zones is one of the theories that could cause them. So there are a number of sort of physical sort of types of transitions in disks where you switch from one heating mechanism to another, or like we have with a dead zone that causes slight change in the surface density profile, and that's enough to do already the trapping.
Okay. So why is it periodic? Like at some.
Yeah, that's a good question. We don't know yet whether it's periodic. I mean, some of these rings in the D-sharp survey are in resonance, but not all of them. So, but we do see some cases where they are really in resonance.
Thank you.
So Ravinder, you can go ahead with your question. Hi, Ravinder.
Hello?
Yeah. Ravinder, can you hear us? Yeah, Ravinder has raised his hand, but I don't know.
Okay, I'm sorry. Yeah.
Yeah.
Okay. Thanks, Ewine, for a very good talk. So my question is, you said these heavy elements in the disk, they settle in the mid plane of the disk, and the gas is in the outer envelope. So, and then eventually this disk material accretes onto the central star. So would it have any impact on the metallicity of the central star, the way this segregation happens?
That's a very interesting question. Of course, the bulk of the star is formed from the direct collapse of the cloud. So the bulk of the star will have the heavy elements that came from the cloud, which are, more or less interstellar values, and interstellar is actually not so far from solar abundances. But what we do find is that the material that accretes onto the stars can be depleted in those elements that are trapped actually in those dust traps. And that's very nice work that has been done by, among others, ALMA for Herbig stars, where the star's atmosphere is not convective, so you can actually see, you can actually measure what is in the outer layers, what has just been accreted. And that accreted material is actually then very poor in certain elements, in carbon, nitrogen, oxygen, maybe sulfur, and maybe some of the heavy elements like iron. They are missing actually from the gas that is being accreted. And it means that they must be trapped somewhere in the disk. And that's actually another very interesting indirect way of measuring what is actually located in these dust traps. So more spectroscopy in that respect as well.
All right, yeah, thank you.
Other raised hands. So any more questions from the participants? Yeah. So if there are no questions, then let us thank Ewine again for a very interesting talk. And we really enjoyed listening to your talk. And thank you all the participants and for a lively discussion. And thank you all. So we'll...
Yeah, and I want to thank all of you, indeed, for organizing this. It was a pleasure to be with you virtually. And also, indeed, good discussions, very good questions. I wish you all the best with your research and with the next, the remainder of your Jubilee week. Congratulations again on your 50-year existence. And I want to end sort of with the motto that we had in our IAU 100 years celebration, which was basically under one sky, and to basically tell each other that we're all world citizens under the same sky. Thank you very much.
Thank you.
Thank you. Yeah.
Thank you so much, Ewine. It was very nice.